All right, this is a Unit 9 lesson on kinetics. Okay, so what is kinetics? Kinetics is the study of how fast a chemical reaction takes place or occurs. Similarly, kinetics can be used to see how far from reactants to products a reaction has proceeded in a certain amount of time. So in general, it has to do with the amount of time a chemical reaction takes or how fast it happens. The proper term for how fast something happens is called rate. So rate is the change in a variable per unit time. In physics, you may have remembered doing distance versus time graphs. And the slope of a distance time graph gives you velocity. Velocity is how fast you're running. It's how much distance you're covering in a certain amount of time. So that's a rate. In chemistry, what we're interested in is two rates in particular. One would be the molar concentration. That's how many moles per liter, how much molar is changing per unit time. If it's a reactant, something that's being used up, then it will be decreasing. If it's a product, something that's being produced by the reaction, then it will be increasing. The other thing that we might want to know the rate of is gases, and gases are measured in terms of pressure. So pressure per unit time, the change in pressure per unit time. So let's do a quick review. Molarity is moles of solute per liters of solution. Solution is the solute and the solvent. So again, think of salt water. It would be moles of salt per liters of salt and water together. That's the solution. Molar concentration per unit time is the molarity per unit of time, or it's moles per liter, the change in the moles per liter per change in unit of time. So for example, how many moles per liter of a reactant are used up in each minute? Or how many moles per liter of a product are produced each second? Those would both be examples of the types of rates of change that we're going to be looking at in this unit. Brackets are used to express the molar concentration. So if you have a chemical compound or a chemical molecule or atom or something inside of the brackets, it means that that's the concentration of that substance. Okay, a rate expression. So here's a rate expression for a reactant A. So the A could be, for example, H2O, it could be CH4, it could be something that's being used up in the chemical reaction. So you say the change in the concentration of A, let's just say it's CH4 gas, per change in time. Now, the reason that you put the negative sign, it indicates that the concentration of the reactant is being reduced. So the reactant is being used up. Now, a rate expression for a product B, and again, the B could be something you're producing, H2O or CO2 or something else, is written delta B over delta T. So change in the concentration of B over change in T. And this expression is positive because products are being produced. So they're increasing in value. So it's a positive number. Okay, let's just take a quick look at how what we're doing in picture form. So this image is called a particulate diagram. A particulate diagram uses symbols for reactants and products. The symbols are shown in proportion to the number of moles in the reaction. So if we look at the top reaction, we see we're starting off with these blue ovals and these red circles. Those are our reactants. Those would represent A and B in reaction number one. Over time, and in this case, they're using the time of 45 minutes, all of those reactants A and B turned into the elliptical shape, the purple elliptical shape, which is C. And you can see in 45 minutes that reaction went completely from reactants over to products, and it took 45 minutes. Now, let's look at the second reaction, D plus E equals F. In this case, the yellow ovals are D and the blue circles are E, and when you put those together over the same 45 minutes, you notice that it produces some of the green ellipses. That would be the product, F, but not all of the reactants went to product. Only some of them did. and some of them stayed as reactants. Now, there's two reasons that could happen. One is the reaction simply reached an equilibrium. That's all the product it wants to produce. It doesn't want to produce any more than 3 of those green ellipses, and then it's happy to sit in that position. That gets into a different subject, one that we're going to deal with after the break, called equilibrium. And not all reactions, in other words, go completely from reactants all the way to products. The other explanation could be that this second reaction is going to go all the way from reactants, D plus E, all the way to F. It just hasn't had enough time. And that's the subject we're dealing with here. So in 45 minutes, that reaction was only able to go part of the way. Maybe the entire reaction will take 2 days for it to take place completely. So that's what these two particulate diagrams are illustrating. Okay, let's look at some rate curves here. And so let's look at these two graphs. So this graph shows the concentration of reactants and products from the beginning of the reaction until time equals 30 seconds. So you can see that down on the horizontal axis, that it goes till time equals 30 seconds. And it could be that the reaction is done at that point, or this graph is simply showing you the first 30 seconds of a reaction. At the beginning, everything is reactant. That's the black line. And there are no products. That's the red line. As the reaction proceeds for 30 seconds, most of the reactants turn to products. So you can see the red line has gone higher and the black line has gone lower. The steeper the line, the faster the concentration is changing. In other words, it's changing at a faster rate. So at the beginning of the reaction, when the concentration of reactant A is the greatest, the reaction moves the fastest because both lines are steeper. You'll notice one line is steep in the negative direction and the other line for the products is steep in the positive direction. So that reaction is taking place the fastest in the first roughly 10 seconds. Then it starts to level off. As you start to run out of reactant, and there's less and less reactant to be converted into product, then the line starts to flatten out. In other words, the reaction does not take place as quickly. But one thing you should definitely recognize on a rate graph like this is that the steeper the line is, whether it's in the positive or negative direction, the faster the reaction is taking place. The flatter the line is, the slower the reaction is taking place. So the reactants line is the steepest at the beginning when the concentration is greatest. The negative slope means the concentration of the reactants is decreasing. And similarly, the product line is increasing rapidly at the beginning when the reaction is the fastest and where the line is the steepest. Okay, and the rate speed is greatest where the slope is steep. So this is a similar type of a graph showing just a reactant, and you'll see that they actually give numbers. So at each of those points, you can measure a rate at each of those points by measuring the slope of the line at that specific point. The line that's touching at each of those dots is called a tangent line. And the triangle is simply indicating that you see that the height of the triangle of the first triangle, the one furthest to the upper left, is greater. So it's a greater rate per unit time. As you go to the right, as the slope of the line gets flatter, you see that the change in concentration gets less and less. So faster is steeper, flatter is slower. Just keep that relationship in mind. And the rate speed is lowest where the slope is less steep. This is a similar graph. This one's for a product because it's increasing as time goes along. A simple point of this graph is that you can use the same kinetic relationships for gases, but instead of molar concentrations, you'll see where the circled axis is, the vertical axis, that kinetics also applies to gases. Instead of molar concentrations, gas pressures P are placed on the vertical axis. Okay, so let's talk about a rate expression and how you can use it to figure out the rates of different reactants or products. So assume that this reaction takes 1 minute to complete. So it's just a simple reaction. It's 2A gives you A2. This could be, for example, hydrogen. You could take two hydrogen atoms and combine them to make an H2, a hydrogen molecule. In 1 minute, 2 moles per liter of substance are used, and 1 mole per liter of A2 is produced. So think about this. The amount of the reactants has to be used up in exactly the same amount of time as the amount of the products is produced. In this case, in this example, we're saying that that's going to be 1 minute. So the rate expression for these would be written as follows. So a change in negative 2A is going to happen per 1 minute, and a change in A2 is going to happen per 1 minute. So in other words, you're going to use up 2 moles of A for every 1 mole of A2 that you produce. Those both have to happen in the same amount of time, which is 1 minute. So these expressions indicate the rate, how fast at which these two processes take place. So let's understand these minus signs. They can be a little confusing at first. The minus sign in the negative 2A indicates that the molar concentration of A is decreasing. That's a reactant. So it's being used up. It's being consumed. You normally don't write, in fact, you never really write that negative sign there. I'm just doing it to illustrate that that is a concentration that is being reduced. The negative sign in front of the expression, that is the negative sign in front of delta concentration negative 2A over 1 minute, that negative sign is written when you're dealing with a reactant, indicates that a rate must be a positive number. So the double negative signs make this rate positive. So since the concentration is decreasing, and that's a negative sign you don't normally write, but since it's decreasing, that's a negative number. The change is a negative number. So if you want to make rate positive, and by definition, rate is always positive, then you have to stick that negative sign out in the front. For the products, it's much simpler since it's increasing. There's no negative signs involved. A2 is increasing, so you don't need any negative signs. It's only on the reactants where you need to do that. Okay, so let's look at this reaction that we have on the left. 2A gives us A2. 2 moles of A gives us 1 mole of A2. What if you wanted to equate those two? And the reason you would want to do that is just so you know at what rate is a certain product or reactant being either used up or created based on how fast another reactant or product is being used up or produced. So we'll see an example of that in a minute. So if you want to equate those two, and notice over on the right, we've put an equal sign between the product and reactant rates. Well, since the reactant is being used up twice as fast as the product is being produced, in other words, 2 moles of A is being used for every 1 mole of A2 produced, if I want the two to be equal to each other, I'm going to have to cut that 2A in half if I want those rates to be equal so I can equate them. And again, the reason we might want to do this is to know how fast one reactant and product increases or decreases in relation to another. So to relate how much of a product is made when a certain amount of reactant is consumed, the two expressions are equated. Since twice as much A is being used as A2 is being produced, the negative 1/2 term must be placed in front of the reactant side to equate the two sides. Normally, the decreasing reactant 2A does not show the negative sign. Instead, inside of the brackets, sign is shown inside of the brackets since it is known to be decreasing. So in general, don't get too crazy about this. Just learn the process. If we have an equation, small a would represent the coefficient, A would represent the compound. So for example, this could be A could represent 1, and small a could represent 1, and large A could represent CH4. In other words, it's some coefficient, small letter, in front of some compound. And that gives you the products AA plus BB gives you CC plus DD. So generally, to write a rate expression for any reaction, the reciprocal, that is, you flip the coefficient, and you place it in front of the molar rate of change of each reactant and product. All of the reactants and products can then be equated. So look at the first term, small a. So you take that coefficient, small a, and you flip it. So it's 1 over small a. And since it's a reactant, it has a negative sign in front of it. And then you simply put that in front of the concentration change in large A, capital A, over change in T. You do the same thing for B. You just flip the B, whatever that number is, you make its reciprocal. Since it's a reactant, you have to put a negative sign in front because it's decreasing in amount, and do the same thing. For the products on the right side, same thing. You flip the small c to make it 1 over small c. You don't need any negative signs because it's a product. It's being produced. That is, its value is increasing. And the same thing for D. So just learn the process. Don't worry too much about the math here. Just learn this process of how you would equate these different components of the chemical reaction. Okay, so let's take an example. So here's BrO3. These are all ions. That's irrelevant. BrO3 plus 5Br minus plus 6H plus gives you 3Br2 and 3H2O. So let's say you're given the value of the rate of change of BrO3. That's the one furthest on the left. Okay. Now, you notice its coefficient, although it's not written, is 1. It does have a coefficient. It's 1. And let's just say that the rate of change of that is 1.5 times 10 to the minus 2 molar per second. So that's 1.5 times 10 to the minus 2 moles per liter per second. And that's at a particular point in time. Let's say that's how quickly that one is being used up. That's the rate at which that's being used up. So the first requirement here is write the complete rate expression for this reaction. So what we simply do is we first write the rate expression for the BrO3, and since its coefficient is 1, well, 1 over 1 is just 1 over 1. And you do put a negative sign in front of it because it's a reactant, it's being used up. Next, we go to 5Br. There it is. And what we're going to do is take that 5 and flip it. So it's 1 over 5. Again, since it's a reactant on the left side of the arrow, you're going to put a negative sign in front. Next, we go to 6H plus, and you're going to flip the 1 over 6, put a negative sign in front of it because it is a reactant. It's being used up. And that gives you that term right there. Now we go over to the product side. We have 3Br2. We're going to flip the 3. We don't need to put a negative sign because that value is increasing. It's a product. And finally, the last one is for water. And we flip the 3 and make it 1/3. And by doing that, we can equate the rates of all of these. So if we want to know how much the rate of one is changing with respect to the rate of another one, we can do that. So we're going to go ahead and do that for this question. So assume that the rate of change of BrO3 is negative 1.5 times 10 to the minus 2. So it's a negative rate. So in other words, that BrO3 minus inside those brackets is a negative number. And actually, I put the negative sign out in front there. So that rate is a negative number at a particular time. So determine the rate of formation of H2O. So now what we're going to do is we're going to go back here down at the bottom, and you're simply going to take the term, the very first term, the BRO, that should be BrO3, the BrO3 term, and you're going to take the H2O term at the end. Those are the only two that we're interested in. And now we'll come back here and we'll simply equate those two since they're already equated in the previous expression. So the complete rate expression can be reduced to the expressions of interest. And that's minus 1 over 1 delta BrO3 over delta T equals 1 over 3 delta H2 over delta H. So the rate that BrO3 is being used up is equal to 1/3 times the rate that H2O is being produced. Why? Because 3 times as much H2O is being produced in a certain amount of time. So if you want to equate the two, you have to divide the H2O production by 3 in order for the two to be equal. Now, since we know that that first term, that BrO3 term, equals negative 1.5 times 10 to the minus 2, we can go ahead and take that, and we can substitute that negative 1.5 times 10 to the minus 2 in there. And what we get is you see down on the bottom. Now notice that the 1.5 times 10 to the minus 2 turned into a positive number. Why? Because that rate, delta BRO3 over delta T, is a negative number. And we put a negative sign out in front, the very front of that, because a rate has to be a positive number. So the double negatives turns it into a positive number. Just remember, your rate is always going to be positive, but when you write it as a reactant, it has to show a negative sign in front in order to do that. Okay, so we simply say 1.5 times 10 to the negative 2 equals 1/3 H2O. Now it's a simple algebra problem. You multiply both sides by 3. And that cancels out the 1/3 on the H2O side of the equation, and you end up with 3 times 1.5 times 10 to the minus 2, which equals 4.5 times 10 to the minus 2. And so that indicates that the rate of H2O is 3 times as fast as the rate of the BRO3. And you could see back on the previous slide, if we go back there real quickly, you can see that up on the top equation on the top, that 3 moles of H2O are being made for every 1 mole of BRO3 being used up, and therefore the H2O rate has to be 3 times faster. And there it is. All right, so that's what the rate expressions are used for. This is not a major part of kinetics, but you should understand how this works. Okay, now we're going to get into what is really is the major part of kinetics, and that's called the rate law. And the rate law is the main equation used in kinetics. Take the following reaction, and we've seen this reaction before. There should be an arrow in between the B's and the C's there. The rate law has the following form. The rate of the reaction equals K times the concentration A raised to some power X times the concentration B raised to some power Y. So A is the molar concentration of reactant A. B is the molar concentration of reactant B. And K is the rate constant, and it's a function of temperature. So the higher the temperature, the bigger K is. And the bigger K is, the faster the reaction is going to take place. So higher temperature puts more kinetic energy into the reaction. This was your glow stick example, and that causes the reaction to go faster. The exponents x and y are determined by experiment. That's a key point. They are not the coefficients, small a and small b. They are shown nowhere in the reaction can you determine by looking at that chemical reaction what x and y are going to be. But we're going to learn how to do that today. Okay, so let's talk about the order of a reactant. It's a term that you'll hear a lot in this subject. The order of a reactant is the exponent x or y on the reactants. So a to the first power has an exponent of 1, and it's usually not written, obviously, when you have an exponent of 1. And this is red. The reaction is first order in A. B squared, it has an exponent of 2. This is red. The reaction is second order in B. And the order of a reaction is the sum of the orders of the reactants. So if you have the reaction down below where K equals A to the first, B to the second, you add the 1 and the 2, you just simply add the exponents together, and that will be the order of the reaction. And the significance of that will be discussed later on, what order of reactions mean. But that means this reaction is third order. The reaction is third order overall. Okay, so let's take the rate law and give a relationship between this. So we're going to just use this example where the rate equals K, concentration of A squared, concentration of B to the first power. So the rate law gives the relationship between the rate, the speed of the reaction, and 1, the concentration in molarity of A, the concentration of B, and the rate constant, which is a function of temperature. Generally, higher temperature produces a faster rate of reaction. There are some exceptions to that, but generally you can almost always assume that that's going to be the case. Okay, so this is a summary of how different order reactants affect the reaction. Let's just use invent some numbers. So So A to the zero power is if the reaction is zero order, then the concentration does not affect the rate of the reaction. Think about it. No matter what number you put in there for A as your concentration, if you raise it to the zero power, you're always going to get the number one. Anything raised to the zero is one. So that means it doesn't matter what the number A is, that term is always going to be one. So that means that a zero order reactant does not affect the rate of reaction. If it's A to the first power, if the reaction is first order, then doubling the concentration doubles the rate of the reaction. If you tripled the concentration, you would triple the rate of the reaction. It's a straight up direct relationship. You multiply the concentration by 10 times, it's going to make the reaction 10 times faster. So it's a straight relationship in that sense. And if you have a second order reactant, A squared, then doubling the concentration quadruples the rate of the reaction. So the increase in rate is the increase in rate is the increase in concentration squared. So example, how is the rate of the following reaction affected by changes in concentrations of A and B? And we're just taking a sample reaction here of rate equals K, A squared, B. So we just invent some numbers for each variable, and we're going to just make ones. So we're going to make the rate constant equal 1, the concentration of A equal 1, the concentration of B equal 1. And if you do that, then what you'd have is all ones, and the rate would be 1. So that's just a base rate that we're using for comparison. So let's just take one at a time. Let's double the concentration of A. So inside the brackets where A is, you're going to put a 2. You're going to double the amount of A you have. And you'll see that if you double a second order reactant, it quadruples the rate. That changed the rate not by 2 times, but by 4 times from what it was in line number 1. So line number 2 is 4 times greater than line number 1 by doubling a second order reactant. If we then put that A back to 1 again and we double B, the concentration of B, that's a first order reactant because it's raised to the first power, then it doubles the reactions. And we said that earlier. If you double the concentration of a first order reactant, you're going to double the rate of reaction. You think about it, what does that mean? It means you're putting twice as many molecules in the liter of solution as you had before. And so there's twice as many molecules to hit each other, and therefore the reaction is going to go twice as fast. Most reactions in nature are first order reactions. They will do that. You put in twice as many molecules of reactant, you get a reaction that happens twice as fast because there's more opportunity for the molecules to hit each other. So conclusions for this example: make all variables equal to 1. That's what we just talked about. That's the initial reaction. Double the concentration of second order A. And what that will do is quadruple the rate of the reaction. Doubling the concentration of second order reactant quadruples the rate speed of the reaction. And then number 3, double the concentration of first order B. So doubling the concentration of a first order reactant doubles 2 times the rate of the reaction. Now we're going to have an example. Write the rate law for the following data. So we're going to take nitric oxide gas, and it's going to react with chlorine gas according to the equation NO equals 1/2 Cl2 gives you NOCl. Just a side note here, you may remember that when you write a formation reaction of a compound, you're always writing it for 1 mole of that new compound. So the NOCl, we want 1 mole, which means that sometimes you might have a fractional coefficient in front of one of your reactants, okay? So that goes back to when we were talking about thermochemistry and enthalpies of formation. You have to write your reaction for 1 mole of the product, and you have to fit all the other coefficients on the reactant side to do that. The following initial rates of reaction have been measured for the given reagent reactant concentrations. Another side note, the word reagent is sometimes used in place of the word reactant. They mean exactly the same thing. Okay, so this is determined experimentally. Remember we said that the coefficients in a rate law have to be determined experimentally. And so here's some experimental data. So let's look at what it's telling us. It's telling us we do one chemical reaction in the lab, and we put into the vessel 0.25 molar NO gas and 1.5 molar Cl2 gas. And what we find is we have a rate of conversion from NO plus Cl2 into NaCl of 1.19 molar per hour. Now we do the experiment a second time and we change the concentrations. So now we have twice as much NO, we have 0.5 molar, and we have the same amount of Cl2, 1.5. When we change those concentrations, we find that the reaction rate is 4.79 molar per hour. That's how fast the reaction is taking place. Now we do the experiment a third time. And this time, again, we have 0.5 molar of NO, and we double the amount of Cl this time, Cl2, to 3. We find that when we have those concentrations, that the rate of the reaction is 9.59 molar per hour. So now we have 3 different sets of data. And with those 3 different sets of data, we can find out the rate law of this specific reaction. So create a rate law in the form of rate equals K times concentration of NO raised to some unknown power X times concentration of Cl2 raised to some unknown power Y. Note, the coefficients in front of the reactant, such as the 1/2 in front of Cl2, play no part in this process. So don't think that they are the exponents or that they have anything to do with multiplying. That 1/2 has nothing to do with it. No coefficient in front of a reactant has anything to do with this process. So first, find the value of X. We want to find that X exponent X on the NO by isolating a change in concentration of NO and the change in rate it produces. Find 2 reactions where NO changes and Cl2 is constant. So what we're going to do is find 2 reactions where the Cl2 is not changing, but the NO is changing. And by doing that, we can see how only changing NO without changing the Cl2 is going to change the rate of the reaction. And if you look, you can find that reactions 1 and 2 meet that requirement. So you see that Cl2 is held constant, and the only thing changing is the concentration of NO. It goes from 0.25 to 0.5 from reaction 1 to 2. And if you do that, what you find is the rate of the reaction changes from 1.19 to 4.79. So create a ratio of NO. And in this case, we decide to put the equation 2, reaction 2, over reaction 1. Why do we do that? Because we'd rather deal with a whole number. 0.5 over 0.25 gives us 2. If we did it the other way around, we would have ended up with 0.5 as our product there. And we don't want to deal with, or a quotient, we don't want to deal with fractions. So you always put the bigger one on top. It just makes more sense. Now, we're going to do the same thing with the rates. So create a ratio of the rates of NO. So for reaction 2, it's 4.79 on top and 1.19 on the bottom, and give or take, it roughly equals 4. Now, note that since the ratio was equation 2 over equation 1 in the first ratio, that is 0.5 over 0.25 was equation 2 over equation 1, then in the second ratio that you also have to make it equation 2 over equation 1. So that's 4.79 over 1.19. So now equate the concentrations and rates with the exponent X. So what you're doing is you're saying the number that you got from the concentration 2, you're going to raise that to this unknown exponent X, and you're going to get 4. So what does X have to be? Well, it's a pretty simple one. That's going to be 2. So the exponent X is going to be 2. So the equation so far is rate equals K, NO, and now we can substitute X with the number 2 that we calculated for X, times Cl2 raised to the Y. We still haven't figured out what Y is yet. So this reaction is second order in NO, a change in chlorine on the rate. So first find the value Y, the exponent for Cl2, by isolating a change in concentration of Cl2 and the change in the rate it produces. So first find 2 reactions where Cl2 changes and NO is held constant. And if you look there, you'll see that reactions 2 and 3 meet that requirement that NO stays the same between those two reactions, but the Cl2 changes. So now we create a ratio just as we did last time between reactions 2 and 3. We're going to put reaction 3 on top. So 3 over 1.5 gives us 2. That's why we did it, so we get a whole number. We could have done it the other way around, but you don't want to deal with decimals if you don't have to. And then now we're going to do the same thing with the ratio of the rates. And we're going to put equation 3 on top of equation 2. So it's 9.59 over 4.79, and that gives you approximately 2, close enough. And again, same thing. Since the ratio was equation 3 over 2 in the first ratio, it's got to be equation 3 over 2 in the second ratio. So now equate the concentrations and rates with the exponent y. So 2 to the y power equals 2. So that's the 2, which is the concentration from the concentration equation, the first equation, to the y equals 2, and that second 2 is the 2 from the rates, the second 2 that you see above. And so y has to equal 1. So the equation so far is this, that the rate equals K, NO, the concentration of NO to the second power, times concentration of Cl2 to the first power. So we figured out both of our x and y exponents. So that reaction is first order in chlorine, in Cl2. So there's the reaction as we have it again up at the top. Now we need to find the rate constant K. That's the only thing we don't know for this. So we do this by choosing one of the reactions and substituting in the concentrations and rate. You could pick any one of these 3 equations you want, but we'll go ahead and just choose number 1, this one right here. So you simply write that equation, but you plug in the concentration of NO for NO, you plug in the concentration of Cl for Cl2, and then you plug in the rate in that particular line right there. So if you see right down there on the lower left, there it is, 1.19 equals K times 0.25, that's the concentration of NO, squared, times 1.5, that's the concentration of Cl2 to the first power. And now you solve that equation for K. You just divide both sides by 0.25 squared times 1.5. And you end up with K equals, you see the equation there, and that equals 12.7. Therefore, the final answer for this, the rate law for this particular equation at this particular temperature, the rate equation is rate equals 12.7, that's your value of K, NO to the squared, Cl2 squared. So what this simply means is if you want to know how fast the reaction will run at this point for different concentrations of NO and Cl2, you could pick any concentration of NO and any concentration of Cl2 and figure out how fast that reaction will run. That's what this rate law does for you. So that concludes our lesson, our initial lesson on kinetics. It's a pretty important one. I guarantee you'll be asked some of these questions on the AP exam, maybe even 2. So know these concepts. We're going to practice these, and we'll do this in class as well. So have a great evening.